Okay, well, happy Monday, and I think I just sent out an announcement that this is for everybody watching online. So Wednesday will be our last lecture. Friday will be, I guess, we'll call that a study day. So I'll be on campus, and if you have any questions about anything, need some help or anything, you can come to office hours, and I'll be happy to try to help you out. But other than that, Wednesday will be our last class session, last lecture. I'll go over what you can expect to see on the final exam, and yeah, that will be that. So this, I thought in today's lecture, and yeah, I guess on Wednesday's lecture we'll have time to cover just a tiny bit of Sklearn. Sklearn is kind of the popular machine learning package for Python, and we really only get it's a huge package, and we could probably spend an entire class covering just a few different aspects of it. Probably one class isn't enough to cover everything, and certainly one 10-week course isn't enough to cover everything in Sklearn, but so certainly 1.5 lectures is not going to be, we'll barely scratch the surface. But let's talk a little bit about Sklearn, and first I thought we'd talk about this idea of splitting your data, your available data, into a training set and a testing set. And so there is there's an application, and I've got just a couple examples of this concept of having a training set and a testing set. Okay, to learn about Sklearn, you'll just go to Google and type in Sklearn, right? And it'll say scikit-learn. This is it, and they break up Sklearn's things into a few big sections: classification, regression. So these would be supervised learning for categorical variables, supervised learning for numeric variables. Clustering is unsupervised learning. Dimensionality reduction is also unsupervised. Okay, and then you've got these tools for model selection and pre-processing. Okay, and so model selection, kind of cross-validation and train test split would fall under model selection. These are ways for us to evaluate how well a model performs. And the goal for a lot of machine learning things, there's a few different goals as far as when we create models and stuff. But when it comes to machine learning, a lot of times our goal is to make our prediction performance, as good as possible, right? So you have so this is a supervised learning situation. Supervised learning means in your data, you start off with answers, okay? So it'll be like these X values come in, and in our data, these are the Y values that get output, okay? And so you might say, well, let's fit a linear regression model. Will these X values come in? Can I predict these Y values? Or, some quadratic model or some other kind of model. When I plug in these X values, can I predict these Y values? And we have a way to kind of measure how good our model is, right? We'll say, okay, well, we predicted this Y hat. The actual Y was this, so we have a residual. And for linear regression, we try to minimize the squared residuals. You might have two different competing models, and you're going to say the better model is the one. At a very, very simple level, you could just say the better model is the one with less squared residuals, right? And have you guys taken 101A? It's not a prerequisite for this class, but Stats 101A, you do like linear regression, and so in 101A, you spend a lot of time on just talking about linear regression, and you see that if you include more terms, if the more complicated your model becomes, generally you can get better prediction performance. Your y-hats get closer to the actual values y. But now you run into the problem of, are you now including unnecessary terms, right? Like that are only going to help you predict this particular data set, but won't help you actually predict anything in the future, right? So for example, in your data set, let's say you had 4 people named John, and they all happened to, I don't know, score, 87 on the exam, okay? And that just happened to be in your data set. And so now in your model, you're like, oh, I could improve my performance if anytime the person's name is John, we're going to predict a score of 87. And you get better performance that way. And so when you evaluate, you say, how well am I predicting? You say, look, by including this extra variable, if the person's name is John, I can now shrink the amount of error I have. Okay, but is that going to apply? Is that a good rule to implement for the larger general data set? And probably not, right? Because this coincidence of people being named John scoring an 87 is probably not something that actually exists in the population. And so when future data points come in, it's going to perform poorly. It's going to predict poorly. And so there's different ways to evaluate whether including an extra term is good or not. And in linear regression, you have all kinds of measures. You have the AIC and the BIC, and you have adjusted R squared, and you have all kinds of stuff. You can do like I forgot what it was called, log likelihood statistic and things like that for to see if things are improving. In machine learning, kind of a common tactic we use is cross-validation, or at least training and testing split. So we have all of our available data, and what we want to do is we don't want to just take all of our available data and create a model based on all of our available data. Because if we do that and we say the goal is to shrink the prediction performance on all of our available data, we might end up fitting extra unnecessary variables. So the way we're going to kind of help prevent this is we split the data, the available data, into a training and a testing set, okay? A training set and a testing set. And then what we do is we fit a model to our training set, and then we see, hey, is this any good? And we evaluate it on the testing set. We say, you know what, when we were trying to figure out our coefficients, when we were trying to figure out which variables to include, we didn't look at this testing set or this holdout sample. And so we figured out which variables to include, and then we can evaluate how well it performs, okay? And sometimes we even further divide it. We'll have a training and a test split, and then we'll take this new training set and we'll split it even further. And within here, we'll have a training and a validation set. And so we can kind of go back and forth between, you know what, should I include this variable for the name John? Is that going to improve performance? Oh, it actually doesn't, right? So it might improve performance over here, but then when I test it on over the data over here, okay, because this wasn't used in the training set, and it says, well, by including that variable John, we're actually making more mistakes. And we say, okay, well, we should get rid of that variable, and we might improve performance that way. So this is almost like a miniature version of testing it on brand new data, right? So, because that's effectively what we want to do, right? We create a model on a smaller set of data, and we want to kind of test it out. Is this working? But in order for it to work, you got to give it data that it's never seen before. Because if it's seen the data before, it can always try to manipulate things to kind of match the answers. So you always kind of give it some new piece of information, in our case, the validation set to see if how well it's performing. Okay, so let's get started. So I'm going to import NumPy, Pandas, Matplotlib, and then from Sklearn there's several a few things. We'll import the linear model preprocessing along with model selection, and then from Sklearn model selection we'll import train test split and cross-validation score. So that takes a moment to load, and we're going to use some train test sets and cross-validation. And so, yeah, we're going to take all of the available data, split it into two parts, and then using only the training portion, we estimate the parameters of several competing models, and then we'll test them out here. Okay. I forgot about our view quiz. I don't even know if I created it today. Sorry. I did not. Okay. I have to, I'll have to create a view quiz today. Let me, I don't know what I'm going to do. All right. Just remind me later. Okay. All right. So we're going to create our predictor matrix X and Y and Z. Okay. And this is just to illustrate how our train test split is going to work. Okay. So here for X, we'll pretend X is our predictor matrix. So I've got 10 observations and I've got 2 columns. Okay, this is not real actual data. Okay, this first array is our X, and this we're going to pretend is our numeric output Y, and we can also imagine it's something where we have a categorical output, a 0 or a 1, and we have a categorical output Z. Okay, and so what we can do is we could do train test split. Okay, and for reproducibility, you can set the random state. And so what I'm going to do is I'm going to take my matrix X, which is 10 rows by 2 columns, and I'm going to say I want 1/4 of my data to be put in the test set, and then the remaining 3/4 will be in the train set. And so it will randomly select, out of the 10 rows, it'll randomly select a quarter of them, so somewhere either between 2 and 3. Okay, it selected 3 of them, okay, to be in the test set. Okay, so here are it selected rows 0, 1, 3, 4, 5, 7, 8, and then to be in the test set, it selected rows 2, 9, and 6. Okay, and if I say I want to split Y, okay, then it will pick the corresponding rows, okay, or the corresponding values. They'll pick 2, 9, and 6 to be in the Y, okay, using random state equals 1. So using random state equals 1, we get the appropriate set. And notice the output of train test split will be 2 values that can be unpacked into a tuple. And similarly, you can do everything in one command here. I'm going to call train test split the same command, put 1/4 of my data into the test size, and I'm going to do both the matrix X and the output Y, all right, using random state 1. And this is going to return 4 values, and I'm going to unpack all 4 values into this big tuple: X train, X test, Y train, and Y test. And we can see when I run that, indeed I get everything. So this will be X train, X test, Y train, Y test. And this way we could see, you know, this matrix of X values corresponds to these things. And that way we can later on, so we'll use these 7 values, you know, along with these 7 outputs to figure out which model parameters are best, and then we could test it out on these 3 values over here. Generally, for a much larger sample, you'll do some a lot larger. Okay. If you got a categorical variable, you can use an argument, stratify equals z, and that will make sure that we get an appropriate number of each category in the resulting split. And I'll just show you what happens if you don't do it. If you don't include stratify. Okay, so you don't, okay, well, we just coincidentally got a, in the output, we have 2 zeros and 2 ones. That was a coincidence. Let me just try something else. Okay, so in this test case, or in this random state, we got, in the output, I have 3 ones and 1 zero, and in the input, the training, I've got 4 zeros and 2 ones. So it's not quite balanced. Whereas if I include this argument to stratify, this will ensure that that the categories are equally correctly represented in the train and test splits, right? So in the original Z, half of them, half are zeros and half are ones, and when we split it randomly, it's going to ensure that half are zeros and half are ones in the training set, and half are zeros and half are ones in the test set as well, to ensure that your proportions are correct. Otherwise, it can make training a lot harder. Especially if you have a categorical variable that's very lopsided. If say only 5% in your categorical output, only 5% matches a certain criteria. In your training data, it could end up getting lopsided where maybe only 3%, and then in the test data, something higher than 5%. It's going to have a hard time predicting all of that. Okay, you know what? I will go ahead and I will insert. Let me just insert a cell here for view quiz answers, and I'll have to. All right, so our first one. What will my first view quiz answer be? All right, we'll do A, and then I'll come back and do number 2, and I'll come back and do number 3 later. But I just have to remember, and then I'll create the quiz. And I'm sorry, I haven't created the quiz yet. But okay, so our first view quiz answer will be A. First view quiz answer will be A. I'll delete this cell later too. All right. What we're gonna do is I've got this this CSV file, and it's just got 2 numeric variables: chemical and magnetic. Okay, and the idea here is we want to kind of test. This is, I guess, from some industrial furnace where they were trying to, purify this iron or something. I don't know how it works. Okay, manufacturing, trying to purify the metals, and they can just do kind of a magnetic test to see, the quality of the metal, and it's quick, it's cheap. And so if they can just get away with using the magnetic test, can they do it? The chemical test, on the other hand, is more accurate. And the question is, does the magnetic test do a good job of predicting the chemical, the more accurate values as found by the chemical test? All right, and so so it's just 2 columns of numeric variables, right? We have a total of 53 observations in 2 columns. And this is kind of the plot here. Okay, here's the plot. Magnetic versus chemical. And the question is, all right, do we just fit a linear regression line? Do we fit a polynomial? What shall we do? Okay. So I'm going to split the data. Okay. Right now, iron is just a big pandas data set, so I could just take iron and split it into train and test. And so train will have, I don't know, these observations, and test will have these observations: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 observations in test. I think. 1, 2, 3, 4, 5, 6. Yeah, 11 observations in test, which means 42 observations in the training set. Okay, so here what we'll do is we will, this is a subset of this, right? So here we took 11 of these observations out, and so now our training set only has 42 data points. And what we're going to do is we're going to try, we'll use only the training data to try out a few different possible models, okay? And so the way we fit a model using Sklearn is similar to the NumPy notation that we saw in stats models. I think stats models was based off of this same kind of idea here. So what we have to do is we'll take X, the X column, which will be our magnetic column, all right? And so that's our magnetic values, and we're going to reshape it into a matrix, okay? And so reshape, what does the -1 here mean? It means I don't know exactly the dimensions of X, right? But I do know is that I know the output needs to have 1 column. How many rows is it supposed to have? I don't know. And so to kind of, because I could say, well, it needs to be 42, 1. But that would require me to know that it has 42 rows, right? And so -1 just says, I don't know exactly how many rows it should have. So NumPy, please figure it out for me, okay? And then for Y, we'll just leave it as a length 42 vector, okay? So X needs to become a matrix. Y can remain as a one-dimensional array, okay, or kind of like a vector. We can see what kind of correlation we get. We get a correlation of around 0.71 between X and Y in the training data, which means our R-squared value is going to be something around 0.5. Okay, we're going to get R-squared value of around 0.5 if we just fit a simple linear regression model. All right, so this is how we would fit a linear regression model. We're going to, from Sklearn, we've imported linear underscore model. That was way back here because we said we're going to make a linear model. So I'm going to do linear model.linear regression. This sets up the linear regression model. And then we're going to fit between X and Y. And with linear regression, it's going to automatically fit a line, okay? And there it says, okay, we fit the linear regression. So we could take this linear model that we've created, we can ask, what's the score here? And it's going to give us the R-squared value, right? And we could say, okay, well, what values did you predict? And we could see, okay, what kind of values did it end up predicting? All right, so we're gonna just take the values 10 through 40 and say make predictions for these things, and then let's plot a line to kind of fit these things. All right, and so we would fit this, and then we could test how well it works. And so to kind of illustrate this concept of training and testing or using cross-validation here, I'm going to use another function called shuffle split, okay? And what we're going to do is we're going to do 5-fold cross-validation. And so rather than just doing one of these things where I kind of say, hey, take a fifth of your data, what we're going to do is we're going to take the entire training data, all of this part, split it into 5 parts, and each of those 5 parts will serve as the validation set. Okay, and so I'll use I will fit it on 80% and test it on the remaining 20%, and then I'm going to do it again, but I'm going to test it on a different 20%. And so let me just kind of show you how this works. So I'm going to do 5 splits, 5 equal parts, and then we're going to do a cross-validation score and just see kind of how this works, okay? And this is all technically we need to do, and the overall cross-validation score I get is 0.471, okay? Because the different cross-validation scores, I got 0.58, 0.53, 0.45, 0.13, and 0.65, and if you take the average of those, you get 0.47. To kind of illustrate what is actually happening when we do this, because technically this is all you really need to do. You don't need to delve in much further. But what I'm going to do is I'm going to illustrate kind of how this is working, okay? And so this is, I wrote up all of this code here, okay? And the idea being we can calculate my the scores that we get here, okay? And so the way it's going to work is we take our x and we're going to split it into x and y, and we're going to split it into training x and training y, and over here I've got test x and test y, okay? And we're going to fit a linear regression model to the training data, and then we fit the test cases to this trained model, and we're going to calculate the mean squares error and the mean squares regression, okay? The mean squares of having no model, which is just the equivalent to just the variance of the test data, and then the mean squares regression is how much did your predictions improve the performance. Is there a way to kind of draw what's happening? Okay, I'm gonna just apologize to those watching the video. Well, okay. Here, let me see if I can just run this and explain what's happening here. Okay, so all of these pictures get fit here. So what we see going on in this diagram, okay? These blue dots for our first data set, okay? These blue dots represent the training set, and then the green dots represent the test set, okay? So if you take the blue dots and the green dots and you add them together, you'll have the full data set, okay? So here's the full data set, and if we take the blue dots and the green dots and add them together, we get the full data set. What we've done is we've fit this red line, we fit the red line to the blue data. And then we ask, how well does this red line do at predicting the green dots? Okay. So if you take all of the residuals for the red line here, all the residuals would add up to 0. But if you take all the residuals here, they wouldn't all add up to 0, because we're just trying to see how well the red line does at fitting the green dots, okay? And so to kind of compare, if you calculate this flat line is what we would consider the null model. The null model is if you did not use a predictor at all, okay? If you had no predictor at all, what is the best line or what is the best thing you would predict? You would just predict a constant. You would predict the mean of the green dots, and this would be your null model. And the question is, does the red line do a better job of predicting the green dots than this green line? And the answer is yes, because if you calculate the mean squared error for this green dot to the green line, and you do it for all of them, you would get a mean squared error of 24.4. Whereas if you calculate the residuals between the green dot and the red line, the green dots and the red line, the mean squared error is 10.23. That's a reduction of 0.58, and that's how it gets the score here. Okay, here is another split. Okay, so this, if you take these blue dots and these green dots, they would add up to the full test set. This is another split between blue and green, okay? And here, because our dots are kind of a little bit more, are different here, the average, if you had no predictor, you would just predict the average of the green dots, which is significantly different over here. Over here, we would predict 18. Over here, we would predict, what, 23? Okay, and the amount of error we would get is 23.5. The mean score is regression. The amount of error between the green dots and the red line is 11, and we get a reduction of 0.53. Here's a different case. Something similar, we get a regression score of 0.45. Okay, I want to just show you this one had the worst regression score. And what's going on is just kind of by random selection, these green dots are spread out in such a way that this red line just doesn't do a good job of predicting the green dots, right? So we just randomly selected a subset of the total data, right? We split the total data, and we put some of them in our kind of our validation set. So the red line does a pretty decent job of predicting the blue dots up here. This is how we trained the model. We said, okay, here are the blue dots, fit the best straight line that you can, and it fits this straight line. And then we say, okay, does this red straight line do a good job of predicting the dots in our validation set? And the answer is, not really, right? You compare, is the red line an improvement over just the flat green line? Just barely, okay? The flat green line would have an error of 17.6, and the red line has an error of 15.2. So that's only an improvement of like 0.136. Okay, and so that's why this error is this score is the lowest, and it's just a result of kind of the random selection that we have here. Okay, over here we have good fit, and so our score is 0.65. And so when you average all of these together, okay, you get an overall cross-validation score of 0.47. And that's your cross-validation score for a linear model. Where did I put the view quiz answers? The first one is A. All right, we'll say the second one is E. Second answer, view quiz answer is E. E is an elephant. E. Okay, let's try one more here. Or a couple more. Here, we'll try quadratic fit, and we'll just see how well all of this does. So our quadratic score is 0.509, a slight improvement. Okay. So here I transform all of my data into a kind of polynomial, and I say, all right, let's try fitting a quadratic thing. All right, let's see how our so the cross-validation score for a quadratic fit, when you do cross-validation, is actually a lot lower, 0.26. And we even get a negative. We get a negative R-squared score, which sounds strange. How could you get a negative score? Okay, so let me just show you. That's the fourth one. All right, so here is the blue dots represent our training data, and the best fitting quadratic line for the training data is this. And then we test it against our test data, our validation set, and we say, oh, you know what? This is not doing a good job. Okay, it's not doing a good job here, right? So how much did it improve over just using a flat line? It improved it a little bit, but the amount of improvement is 0.204. Okay, and we can see how much our fitted line changes depending on which points get selected in our training set. Okay, and so this time, because of a different random selection, it fit this line. okay? And how well does this perform? Well, here it does a good job. I mean, kind of a good job, okay? It goes, if we just used a flat line, we would get a mean squared error of 23.56. By using the red line, we improve our predictions to 14.29. So that's improvement. Okay, here's a new training set. This is the best fitting line for the training set. If I use that same line over here, I get some improvement. Okay, and this is where this is where things go bad. Okay, so here is the training data, and this is the best fitting quadratic line for the training data, and here it is for the test data. And if I use the same line that I fit on the training data, my performance actually gets worse. The green line doesn't do a great job, but it gives me a mean squared error of 17.6. If I calculate how far off my values are, okay, and here it doesn't seem like it's doing all that terrible, okay, but because I've got some values that are quite far away from the line, like this dot is far away, this dot's really far away, and this dot's pretty far away, and this one is also really far away. This dot, this one dot, does a really bad job there. Because of that, my mean squared errors regression for the red line to the green dots, and it's probably caused by this one right here. I actually end up having a higher score. And so, did it improve at all? It didn't. It actually got worse. Okay, and so now I'm getting a negative r squared value. Okay, and it feels strange getting a negative r squared value, but the r squared is kind of how much did your predictions improve over just predicting a flat line, right? Because if you were not going to use any kind of predictors, you would just use a flat line, and that's kind of like your minimum standard of prediction. I'm just going to predict a constant for everybody. I'm just going to predict the mean for everybody. And any model you use has to outperform just predicting one constant for everyone. And here we're actually doing a worse job than predicting a constant for everyone. And that's why I'm getting a negative r squared score. Okay, at least over here we're getting a lot more improvement. Okay, because this dot creates a lot of error for just using a constant. Okay, this dot, which is super far away, creates a lot of error for using a constant. And I'm shrinking that error by using the red line, which does a good job of closing that up. Same thing with this dot down here. Lots of error for this dot down here. The red dot kind of reduces it quite a bit. So we get a 0.58. But we can see that, when you use the whole data set, it can be misleading. You think like you get quite significantly better performance. But it's when you look at kind of splitting the data and doing cross-validation, you realize, oh, you know what? Quadratic fit might not be the best. And things kind of get just even wonkier as you go higher into higher order fits. So again, if you use the full data set, your r-squared value keeps getting better, okay? But is it truly better? Okay. But when you do cross-validation, all right, so here we get quite a bit of negative performance. I get negative 0.8. I got really bad in the second one, okay? So let's just see what happens. Yeah, we can see what went wrong, right? So in this second example, the training data, somehow this is the best fitting cubic model for this training data. And we can say, okay, it doesn't even look good for this training data, on this training data split. And then when I try to fit it to the test data, we can see it actually did really, really bad because this point is up here and we're predicting way down here. And remember, when you use squared error as your basis of measurement of performance, squared error really punishes big differences a lot more than small differences, right? Because if you had, squared error, if you had 10 errors of 1, your total squared error would be 1 squared times 10, 10. Okay? But if you had 1 error of 10, your squared error would be 10 squared, 100. Okay? So squared error really punishes big differences a lot more than small differences. It would much rather have 10 errors of 1 than 1 error of 10. And so here we're basically getting one error of something really big, one error of like 18. Okay, so this is huge. Okay, and so it's getting punished a lot, and so its mean squares regression for this is a lot more than if I just used a flat line. So here I get a negative R squared score. So we can see that using a cubic model is just not good. Right? And when we look at all of these things, we can say, oh yeah, this is not doing a good job. This is not doing a good job. This looks like it's doing an okay job, but it turns out it's not better than using a flat line. We can say, okay, yeah, this is not doing a good job, and look at that. Yeah, indeed, its mean squared error is quite terrible. Okay, and if we just keep going here, here it is with 4 degrees. So here we actually, same kind of stuff. Okay. 5th degree polynomial, yeah, this is doing a really bad job. We get a score of negative 390. Okay, oh yeah, somehow. So yeah, when you fit a 5th order polynomial, the extrapolation goes terrible, right? So here, because all of my data set was in this range, it didn't know how to go, and so with the polynomials, they just kind of rocket off in different directions. And just because in this train test split, my training data ended at 30, but in the testing data, it keeps going to around 40. So here we get a huge amount of mean squared error, like a ridiculous amount. And that's why my score, this one's 393 times worse, the amount of error that I'm generating. It goes from 23 to 9,000. Okay, so we're like almost 400 times worse here, and so anyway, that's what's going on. So the thing is yeah, anytime you fit just if you're using the full training data, you can be misled into believing that using more complicated models, higher order polynomial fits is going to improve your performance. And it might appear that way, but then when you do cross-validation, it uncovers kind of the truth in that that kind of split is not going to do any better. Okay, I've got A and E and our last view quiz answer. Let's go ahead and do C. Okay, A, E, and C. And so I have to actually create the view quiz, so give me a minute to do that. But we'll end here for today. We'll see you guys on Wednesday for our last lecture, and then that's all. Have a good rest of your day, and we'll see you later.